Alright, this is just going to be a video on the dot product and how to use it. So if you do remember from earlier, we do have some things that we can do with vectors, and the dot product is a sort of multiplication of vectors. So if you recall, we can add vectors. So let's say we have this u vector plus a v vector. This is pretty easy. You just take their components, and this will be a plus c and then b plus d, right? And let's see, add vectors, and you can subtract. So similarly, we can multiply vectors, and there's two types: the dot product, which we'll be looking at today, and the cross product, which we will not be looking at today because that is mostly just used in physics. So basically, the premise of the dot product is a vector, remember, has direction, but a scalar does not. And the whole point of the dot product is when you multiply these two vectors together using dot product, you get a scalar quantity. So it's just a number. Let me highlight this. It's a number, not a vector. So it doesn't have anything direction-wise associated with it. It just describes the relationship between two vectors. So as you can see, the way you would use this is, let's just say we have u vector, v vector. U dot v is equal to the components dot components, which is equal to AC plus BD. And this gives a number, like it's like 5 or something. It could just be a number. There's no components or anything. It doesn't result in something that is in this format. So this does not turn into something that can be represented as such as that. So this does not happen. And let me just do that in red. That does not happen. So if we go back, just remember it's pretty similar to the addition one, except that it's no longer in this form, and then you multiply these and then add together. So that's pretty easy. Actually, let me just keep those in because those are nice. So let's first look at some properties, and this is all based off of the completed notes on Mr. McGow's math website. So I'm just doing like a video about them. So there are some properties that will make a good amount of sense, and they're pretty obvious. So the first one is if you have u dot v, this is equal to v dot u. So it doesn't matter, because if you think about it, let's say we have our a and b like this, right? And then c and d. It doesn't matter if we go a times c or c times b, c times a, because that's just the same as one regular multiplication. So that's one right there. And then the second one is going to be the distributive property, which is a little less intuitive, but still makes sense. So if we have v vector, and then let's just say we have r vector here, like this, and they're added, and we dot product right here in the middle, we're going to get u dot v plus u dot r. And I should probably use a darker pen. All right. And the most important one by far is if we take the dot product of itself. So we have u vector times u vector, dot u vector. I'm sorry. Times is not the right word to use because dot product is something different. If you recall, this means magnitude. If you use absolute value bars, you get the magnitude squared. And this is really important because this is what helps us find the most core use of the dot product, which is the angle between two vectors. And you can just quickly prove this, because say we have AB, right? So this is our component form times, or sorry, dot AB. Using our idea about the dot product, we get a squared plus b squared. And if you remember, or if you recall, this magnitude of any given vector is equal to its first component squared plus its second component squared, all square rooted, because if we just have any u vector like this, it will have component A and component B, and then we can use Pythagorean theorem. So this actually ends up being the magnitude of u squared. So this is really important to remember. This is fundamental. And some more basic ones would be like if you multiply u vector times a 0 vector, so just a point, you get 0. And you can also do multiplying by scalar quantities. So if you had like c times, like actually times, not dot producting, like u vector dot product v vector. This gives scalar of u times v, like this. So c is the scalar. And this is just similar to the scalar multiplication. So remember, when we get that final number quantity, you multiply this by c. So this will be this here will be multiplied by the c here, and that'll give another number. So I'll do the a and c because a is sort of the same as b. It's just a different application. Well, okay, so b would be showing this one, this property where you're multiplying by scalar. A would be showing this distributive property, and c is actually something different. So I won't do a or b. You can find those on the completed notes. But for c, this one's sort of important. So this is going to be dot producting here. So we have u like this. I'll just rewrite it, and then we actually do know the magnitude of these two vectors. If you have 4, 3, remember Pythagorean, so this will be f5. And then if we have if we have v like this, and we take the magnitude, that'll be 13. Just remember your Pythagorean triples from here. So from here, you can actually remember these act as scalar quantities on the vectors. So we get 4 over 5, comma, negative 3 over 5, dot product, and then we have 5 over 13, comma, 12 over 13. And this is going to be our dot product that we need to take. So we were going to get 4 over 5 times 5 over 13. Remember, a times c, plus the negative 3 over 5 times the 12 over 13. Oops. And this will give our dot product that we want. And if you calculate this out, you're going to get negative 16 over 65. So yeah, then as you can see, it's just a number. There's no stuff, I guess you can say. Anyway, besides that, we have the most important use of the dot product, which is the angle between two vectors. So if you recall, if we just call this u vector, and we call this, actually let's call this a and b because the notes do it that way. A vector, b vector, and then this is theta. We know that this vector here is going to be a minus b. So if you recall our law of cosines, let's call this side c. We have c squared equals, let's call this a squared and b. That's side a. C squared is equal to a squared plus b squared minus 2ab cosine theta. And this applies with vectors too. So actually we can do it pretty easily. And these are all magnitudes, I should mention. These are lengths. So when we take into the vector account, we actually get something like this. So remember, whenever you do the length of a vector, it's its magnitude. So then we're going to get a like this squared plus b like this squared minus 2ab cosine theta. And I should mention that these are also magnitudes. I should not forget that, because that is important, because these magnitudes are numbers. Just to remind you again. Okay. Now from here, remember that this resultant vector here is actually just one vector, so we can probably actually call it r, or we'll call it c vector, because it's easy like that. So what would c vector squared be, the magnitude of it? Remember from our very first, actually no, we can't call it c vector because this is minus. I messed up. That's my apologies. So when we do this a vector minus b vector, we might want to go back to this important property of when you square a vector, you actually just get the dot product of it twice. So this becomes dot product like that. And then this one becomes dot product of itself again, which is A dot product A minus B dot product B, like this. And actually, we don't even need to do this. I'm forgetting how to do this. Actually, no, we keep this the same. That's right. We don't need to do any of that fancy stuff just yet. So that we have this. And then let's take the dot product of this, and we're going to use our distributive property. Or actually, this can just be a... because the dot product sort of works like multiplication before you actually calculate it, we can do our difference of squares here. So we're going to get A dot product A like this minus B dot product B. But notice I'm not squaring anything because these are actual vectors and they're not magnitudes yet. And this is going to give and then sorry, we need a like this. It's just like any other normal expansion. And then there's a dot product. And this 2 is actually a scalar quantity because we're minusing it twice. So from here, remember, when we square a vector, we end up getting the magnitude squared, just like that. So we're going to just use the opposite of that last one. And notice how with this, we're actually going to be able to cancel out these on both sides. So what we end up with is negative 2A dot product B like this is equal to negative 2 magnitude A magnitude B cosine theta. And we can just cancel these negative 2's, right? So A dot product B is equal to magnitude of A, which is a number, times the magnitude of B, which is another number, times cosine theta. So the angle between two vectors is given by the dot product divided by their magnitudes times multiplied together. And remember, the dot product is a number, right? And this is also a number. So that means we can actually take the inverse cosine of this. So we can get theta is equal to arc cosine, or cosine to the negative 1, of this value. And I'm sorry, all these like things are supposed to be vector. So these are really important to know. And I'm just going to put this in here. So this, just to really emphasize this, cosine theta is equal to the first one dot product the second one over their magnitudes. And this is quite important to remember. And I'd like to note that the bottom one is them multiplied together because these are already two numbers, and then the top one is actually a dot product. So yeah, don't forget that. And if you're a little keen, you've probably already noticed this already. If vectors are 90 degrees, that means one thing is 0, right, for this one. So this one, actually, the y is 0, and we have some x for that. And then this is the x is 0, and then there's some y for the component. And if you multiply x times 0, you get 0. Y times 0 is 0. So if we have vectors that are at 90 degrees, so let's just say u and v are dot product, and they're at 90 degrees, we should get a 0 for the dot product. So we can say that if the dot product between u and v is 0, if and only if it is a 90 degree angle. So theta equals 90. So if you ever get a dot product that's 0, it's really easy to tell that it's perpendicular. Or if it's perpendicular and asks you the dot product, boom, it's 0. So we're going to do some more of these like problems, so to say. I'll probably do the first one, and then you guys can deal with the other ones. But it should be pretty obvious about what's going on. So first, sketch the vectors of the plane. So this one's pretty easy. 2, 3 is like somewhere around there. And then negative 3, 2 is like somewhere around there. And if you notice, that should be a 90 degree angle. This should equal 0. This one, we have 1, 1, and then negative 1, 1. That should be 90 degrees, so this should be 0. This one is slightly different. Don't get tripped up. We have 2, 4, negative 2, negative 4. This should be 180 degrees. So if we find the dot product, it's going to be 2 like this. Dot product negative 2, negative 4 like that. So we have negative 4 minus 16 is equal to negative 20. That's their dot product. So from here, we have the magnitude of A is equal to 6, magnitude of B, 12. So we know that theta is this. So just remember that dot product like this is the answer we want, and it's equal to the cosine one like this. So this one's pretty easy. So 6 times 12 times cosine 135, and that should be negative 2 rad 2, like that. So this is going to be equal to 36 rad 2 over 2. Oh shit, rad 2, just rad 2. And then don't forget your negative sign. And that should be the right answer. But if I get any of those wrong, it's okay. I should. You guys should be able to correct me on that. Anyway, so the next thing that we need to notice is work. So work is pretty important. And it's very important in physics. So if you ever want to take that class, this will be a great head start on how to get used to that. So a horse is pulling a cart, and a student lifting her backpack from the ground, pushing a shopping cart, a weightlifter pushing a barbell over set. All these situations can be described by work, which is correct. It's energy. The ability to do work is energy. And then this can be calculated using dot product. So that's pretty nice. So work is equal to force dot product times displacement. If you notice, if you've taken physics, this is just the definition of work. Work is equal to force times change in x, and change in x is displacement. But the problem is this is in 1 dimension. So if you want it in 2 dimensions, you need to take the dot product of the vectors, because both force and displacement are vectors. So this actually gives a really good demonstration of why this works. So force dot product displacement is equal to magnitude of force times magnitude of displacement times cosine theta. So usually force is used in newtons. This is the quote unquote most basic unit for force. Pounds are imperial units, so that's usually not used. And then displacement is in meters, and then feet, which is also imperial units. But I would probably think it's better to use metric in this case. And just important note, if you want to take physics in the future, joules are what used to measure energy and work, and yeah. So if a person lifts a package weighing 75 newtons, let's write that down, and she lifts it 1.2 meters off the floor, what work has she done? So this one is pretty easy if you think about it. So how much work has she done? Work is equal to the force, which is 75 newtons, times the displacement, 1.2 meters. And this should give, if I grab my calculator, 90. She has done 90 newtons of work. I'm 90 joules of work, my bad. And the reason I just multiplied them straight on is because this is in 1 dimension. They're both pointing in the same direction. So I don't need a dot product anything if they're in the same direction. Because a package, the force of gravity pulls it straight down, and supposedly she's lifting it straight up. So this is in 1 dimension. So yeah, it all works out. However, this second question is a little more complicated. A sailor pulls a boat along a dock using a rope at an angle of 60 degrees with the horizontal. So that should look something like this. If we have our boat here, and then the man's here, and then he grabs the rope, and it's 60 like that. And he's standing on the dock. Look at our man standing on the dock. Okay. How much work does a sailor do if he exerts a force of 255 newtons on the rope and pulls the boat at 3 meters? Pulls the boat for 3 meters. So, like I said, work is going to be equal to the force vector times the displacement vector, or the magnitude of the force vector times the magnitude of the displacement vector times cosine theta. And this second one is what we'll be using right now, because we know the angle conveniently. We know that he exerts 255 newtons of force, and the exertion is always done at the angle that it's happening. So that's the length. So we know that's the magnitude. Then we multiply it by the distance that it gets pulled, which is 3 meters, times cosine 60. And if I just remember that right, that's 1/2. Yeah. Okay. So we have 255 times 3 over 2 joules. And that's our answer. And I'm just going to calculate that on the calculator real quick. And this gives us 382.5 joules. So that should be our answer. Anyway, moving on. I will let you guys do the next two because these are A and B. These are pretty much the same as what I described here. And that's pretty much it that you need to know for that part. There's something a little different called resolving forces into components. So like anytime you have a force, so this is mostly a physics thing, but I guess math also uses it too. But when you have a force vector, it's easy and it's good to break it up into components so you can see which direction things are going in. So a really great representation of this is something on a slope. So the force of gravity, for you physics students out there, pulls straight down towards the center of the earth, which is the same for everything. But the thing is, how is it possible to find the force going down the hill and the force that the car exerts on the ground? Because remember, there's always an equal and opposite force, right? So the car has to exert some sort of force onto the ground. And if you take physics in the future, you'll notice that this is called the normal force, which is perpendicular to the position. So basically, how do we find this and that? Well, if you look at it, this is actually 90 degrees. So we just happen to really conveniently break this up into components. So this is the component of the weight vector, which one component is pointing down the hill and one component is pointing straight into the ground. So it's pretty well explained in this, so I'm just going to let you guys read that. But I like this last example, this last sentence, because it makes it really intuitive. The steeper the street, the more force the brakes have to put into the ground because there's more force pulling it down. So that's pretty good representation of that. Anyway, so I'm just looking at what would be good to do. This all seems pretty manageable. So hopefully with everything I've already said, this should be okay. As far as the explanation goes, the video is done. There's nothing else I really need to explain. But if you want, I will stick around and I will do some of these problems. So yeah, thanks for watching and let's get to the problems. So let's say Rocket is pushing a block up a hill to get stronger. He decides to take a break and his friend Alan holds the block in place while he rests. If he is applying 100 pounds of force on the block, how much does it weigh? Assume the hill is at a 20-degree incline and the block and hill are both smooth and no friction. So being a physics student, this is actually really helpful because there's no friction. But this is quite a simple block and hill problem. So let's see. If he's applying 100 pounds of force like this, that means it's in equilibrium right now because it's not moving. So if we were wanting to solve this, let's first break it up into component, right? So we want to know how much it weighs, which means we want to know the force of gravity. So let's draw the center of mass here, and let's just say this is the force vector of gravity. Let's call this force G, for force of gravity. So obviously, like I said, there's the component that pushes straight into the ground that goes this way. And then there's a component that goes down the hill, which is that way. And we'll call these V and U for convenience sake. If this is 20 degrees, this is also 20 degrees. And that just can be found with some geometry. And we also are given that U is 100 pounds because he has to apply 100 pounds of force. So negative U is equal to 100 pounds of force on the block. That means U is equal to negative 100, assuming that the down is negative, right? So if we just want to find the magnitude, we know the magnitude of u is equal to 100 because the absolute value of negative 100 is 100. So we can take sine of 20 degrees to get u over this fg, which I guess is equal to w because it's the weight vector. And these are all magnitude values, right? So we want to know what the magnitude of this weight value is. So we're just going to swap. We're going to swap these right here. So we're going to make it like this. And if you calculate this using the numbers we're given, which is 100 over sine 20, you get something around 292.38 pounds. And that is how much the block weighs. And that is not the force needed. That's just how much, if you were to put it on a scale that's flat on the ground, how much it will show up. All right. So for 6, here's a car drives 500 feet on a road that is inclined 12 degrees to the horizontal as shown on the figure below. The car weighs 2,500 pounds, and gravity acts straight down on the car. Like I said, gravity always acts straight down, with a constant force of negative 2,500 joules. So this is a really common physics problem as well. So first is find the force experienced by the road due to the weight of the car, which is what I was talking about. If you split it up into its components, there's the one that goes straight into the ground and the one that goes down the ramp. The one that is going straight into the ground is the force that the car exerts on the ground. And that's due to its weight. So if we know that this is 12 in here, and we'll just call this the v vector, and this is u vector, and this is, we actually are given that this is force vector, so I should probably write that. We can take some, we can do some simple sine, cosine stuff. So we know that the magnitude is equal to this, right? And we also know that cosine of 12 degrees is equal to the magnitude of v vector divided by the magnitude of f vector. So if we just do some multiplying here, we can find that v vector is equal to 2,445 pounds. And this is the force that the car exerts into the ground. Now, the other one is the work done by the car in overcoming gravity. So how much work does the car need to do to be able to stay on the road without rolling down the hill, right? And that, in this case, is our u vector. So let me just label this A and B. That means we need to find that u vector. So we know that u vector over f vector is equal to sine 12. And once again, cosine 12. Yeah, no, this is sine 12 degrees, my bad. And if we just do some simple math, that is going to give us 519 pounds. No, 520 pounds. And that's how much force the car has to go in this direction to overcome gravity going down. So, yeah, that's pretty much it. There's this last one that is basically just a rewritten version of what I showed above. And the premise is sort of, if you can, in general, the component of u onto v can be described by using the dot product. So this can be found using this formula. And actually, I guess I'll put it into use here. So component of u vector onto the v vector. So like, you see how we have our u vector here, and then this is the component that's on the v vector. So that can be found like this, and this is just like this really weird subscript spelling. I don't get what's going on here, but just remember, it's sort of the same thing as the dot product, remember? To go to u dot v, but we're just moving this v over here. And that's basically it. It's just finding the component of u that's along the length of v. And I'm not sure if it's a high use case, but that's just the general premise. And the problems regarding it are usually quite simple. So yeah, other than that, that's all you really need to know about dot product. If you have any other questions, just let me know and I'll try to get to them. Thank you.